Okay. Hi, everyone. Thanks for making it to my talk. I'm so glad that you're all here, and I hope you're not so exhausted from these 2 days of this awesome conference. And you still have some mental capacity for my talk today, which is titled Decentralized Storage with IPFS, How Does It Work Under the Hood? But first, a few words about myself. So my name is Dennis. I'm a research engineer at Procore Labs, who's the driving company behind IPFS and also other projects you may know, which is called libp2p or Filecoin, multi-formats, IPLD. If you're in that space, you may have heard about all of that. I'm also an industrial PhD candidate at the University of Göttingen, so there's this research part as well. And I'm in the Web3 space since 2020, and you can find me on the internet through all these handles here, on GitHub, Twitter, the web, or via email. So if you have any questions, just reach out through any of those. So what's the agenda for today? First, I will cover what IPFS is. So maybe raise your hands if you have already worked with IPFS before. 1, 2, 3. So, OK. But I imagine, since you're here at this talk, you know what IPFS is. Maybe raise your hands if you have heard of IPFS before. OK, great. Awesome. Yeah. Anyway, nevertheless, I would just cover briefly what IPFS is, and at that point, after that point, I will just assume we have installed an IPFS node on our local machine, and then I will go through some of these commands that you can do, and we will import some content to your local node. Then we'll connect to the network. I will explain content routing. That's the very technical part, and at the end, I will share some details about a measurement campaign, which is part of my research. So, what's IPFS? In words, IPFS stands for the Interplanetary File System. And IPFS is a decentralized storage and delivery network which builds on peer-to-peer networking and content-based addressing. And one common misconception is, that I also heard yesterday night, is the question, is IPFS a blockchain? And that's a clear no. IPFS has nothing to do with the blockchain and is not using anything like that. In numbers, IPFS is operational since 2015. It serves far more than 1 billion requests per week, serves hundreds of terabytes, and we can also observe tens of millions of active users, hundreds of companies built on top of IPFS in all of these domains here at the bottom. And these are estimates just from our own vantage point, so at Procore Labs, and since no one has a clear view of the decentralized network and can assess all the things that are happening, these numbers are likely even higher. So what's the value proposition? So what aims IPFS to solve? The main thing that IPFS does is it decouples the content from its host. So it removes powers from gatekeepers that are gatekeeping the data of users or whatever. And it does this with a concept that's called content addressing. And I will get into content addressing in a second. Those content addresses, these are just links, and they are permanent and verifiable, so anyone can serve content to you, and you can check that the content you got served is actually what you requested. Since IPFS is decentralized, it's also very censorship resistant, and it also alleviates backbone addiction. So what do I mean with that? Let's imagine we are 100 people in this room, and every one of us is downloading a 100 megabyte video from YouTube. The internet, so we would put pressure on the backbone worth of 10 gigabytes. But instead, with IPFS, since it's a peer-to-peer network, we could just transfer that file once into this room and share it among each other, and remove some pressure from the backbone in this case. And also offline friendly. So if we were to work on a Google Doc document in this room, why shouldn't we be able to continue working if we lost internet connection? And also for emerging networks, in the case for, let's say, natural disasters or so on. So it's very network partitioning tolerant. So now I will assume we have just downloaded IPFS and installed it on our node, but there are actually several ways you can do that. So you can download the IPFS desktop bundle, which is just a convenient way to get started. So if you're not familiar with that, you can also add a browser extension, which can then just resolve those IPFS CIDs for you. Or you can just use Brave or Opera, which comes with a bundled IPFS node straight away. For this talk, I will assume we have just downloaded the command line tool, and we will just operate on the command line, since it's a developer conference. And there's actually not just one IPFS implementation, but also, so IPFS is just a specification, and the most common reference implementation of that specification is called Kubo, which was just renamed a couple of weeks or months ago and was formerly known as Go IPFS. Another implementation would be IRO, which is quite new, and this is a Rust implementation. So we have installed IPFS, and now we will just start adding content to our local IPFS node. How does that work? So we will import content. First of all, we will initialize our IPFS node by running IPFS init. This will trigger the generation of a public-private key pair. And you can already see here, this long string of characters is our peer ID, which will become important later on, or basically throughout all the interactions later. Then this IPFS command also initializes a .ipfs directory in your home folder, which just serves as a point where you store content that you get served from the IPFS network and so on. Also stores configuration and so on and so forth. And this is also just a local operation, so we haven't communicated with the network at all at that point. Then we will start. Let's just add a file to our local IPFS node here. And I just chose the Kubo gzip file here, and we will run IPFS add, and then the file name. And then there's a progress bar, and this progress bar, when that finishes, we will get this content identifier that I already touched on a little bit earlier. This is this long string of characters. And this is the most fundamental ingredient for the whole IPFS system, because this is the point where it decouples the content from its location. And as a mental model, you can think of this CID as a hash with some metadata. And these CIDs have some very nice properties. One is it's self-describing, and you can see this here at the bottom. The CID is actually quite sophisticated and consists of several different parts, like a base encoding of that CID and a CID version, because there's version 0 and version 1, multi-codec and multi-hash. And all these different codecs and hash functions are all specified and defined in another project that's called multi-formats. And this project governs which hash functions can be used and how this whole structure looks like. These CIDs are also self-certifying, and this means so in the content is not authenticated by its address, like an HTTP with its URL, but it's certified by its identifier itself, and it's also immutable. So if you have a terabyte large file and just change one bit, you will get a completely different content ID. But since this talk is called "How does it work under the hood?", we will just look what actually happened here. So IPFS has taken that file, which is just this white box, this stream of bytes, and has taken it apart into separate chunks. So it has chunked the file in different pieces. And chunking is basically used in many traditional networking, network communication. Is a common technique, basically. But this also provides some extra benefits that are stated here on the right. So I will just highlight those three. So the first one would be piecewise transfer. So we can just piecewise transfer that file without transmitting the whole thing. Then it also allows deduplication. So if we end up with chunks that are identical, so in this case, these two green blocks here, these this depict two identical chunks. We can do something that's called deduplication and optimize storage in the back, in our repository, which is this .ipfs folder. And we can allow random access, and random access would be necessary, for example, if we watched a video and just wanted to start at the second half, we didn't need to transmit the first part of that file just to get to that point there. But still, so now we have these different chunks, but we still want to operate on a single file. And what now happens is we take those chunks and construct them together again. And we do this by hashing those chunks and take each of those hashes. Let's from this green chunk and this red chunk, we hash them. We create also a CID, so they are addressable by on their own. Then we create an intermediate node, which embeds those CIDs, and this intermediate node again is hashed, and the CID is created. And we do this for the other two blocks here, and we create an intermediate node, and then we take those CIDs from those two nodes and combine them yet again, ending up in this root here. And the CID of this root, that's the final CID that we will work with. That's the CID that's here in this red box at the top. This is also called a Merkle tree data structure. However, this is not what IPFS uses, since we have two identical blocks at the bottom, and in Merkle tree technically cannot have two different, a Merkle tree node cannot have two parents. It's actually called a Merkle DAG, and DAG here stands for directed acyclic graph. But that's just a detail, and all this chunking and combination of these chunks is again governed by another project that's called IPLD, and IPLD stands for Interplanetary Linked Data. And this also encodes things like how do we structure directories and not only files. Okay, so now we have initialized the IPFS node and added a file. But the file is not available on the network yet because we still have not connected to any other nodes. And though even if we were already connected to the network, the file would still only reside on our local machine. But let's take a look at that. Let's connect to the network now. So, oh, okay, not quite right. But yeah, we connect to the network with the IPFS daemon. So we just run in our command line IPFS daemon, which is just a long-running network-connected IPFS node. Some versioning information is printed. The swarm information is printed, which is just a list of the network addresses that we are listening on and ports. And then it's announced to the network. And at the end, this daemon process tells us that it started an API server, a web UI, and a gateway for us. So this web API server is just an RPC interface, which is used to control the IPFS node. And the web UI would be the thing that you saw with the IPFS desktop version, just a UI to interact with that node. And a gateway, which is also an interesting thing, is a bridge between Web 2 and Web 3 in this case IPFS, because you can use the HTTP protocol and add a CID at the end of the path. And this endpoint will translate that to an IPFS query and resolve that CID for you from the network. And then the daemon is ready. So now we have added a file, we have connected to IPFS nodes, but how do we do that? So we have a CID, how do we know which host in the network actually stores that content? And the solution is quite simple. We just have a very large table which maps the CID to the peer that's providing that content, right? Well, as I said, we're chunking those files, and each of these chunks also have their own CIDs. This table gets humongous, so that's not possible to be stored on just one single node. So the solution would be to shard that table, or split it and distribute it to all the participating peers in the network. But then again, how do we know which peer holds the share of that table? And the solution to that is actually quite interesting. So we just deterministically distribute those pieces based on a mechanism that's called Kademlia, and Kademlia is a distributed hash table that's called DHT. And now I want to do an experiment. So all the other talks about IPFS usually just skip over this DHT part because it's actually quite complicated, but I will try to give some insights how this actually works. And so bear with me, but at the end I will just summarize it again, so that's where you can jump in again. This whole process is called content routing. So how does content routing work with a distributed hash table? IPFS uses an adaptation of the Kademlia DHT. It uses a 256-bit key space, and this means that those CIDs that we saw earlier and peer IDs are again hashed to just have a common key space for both of these entities. And the DHT in general is just a distributed system that maps keys to values, as we've already seen, and it's just a 2-column table. And the most common records, or important for this talk, are the provider records and peer records. So provider records and peer records. The first one maps CIDs to peer IDs, and peer IDs, and the second one peer IDs to the actual network addresses. So if we want to resolve a CID, we need to do 2 lookups. And the key features, the key features of this Kademlia mechanism is, so there are two key features. The first one is the XOR distance metric, and this just means if we have 2 keys, 2 256-bit keys, and combine them together via XOR, we end up with a new stream of bytes or bits. And this operation actually satisfies all the requirements of a distance metric. So we have a notion of closeness. So we can tell peer ID X is closer than peer ID Y to a certain CID. And this is not closeness in geographical terms, but in this key space terms. This is the first key feature. And the second one is a tree-based routing. This is depicted on the bottom right here. This is from the original Kademlia paper. In this case, we are the black node here, and there are several other white ones here. And this tree-based routing just says this black node needs to know one node from this bubble, one node from this bubble, and that one here. And only if it knows just one of those things, one peer from these other bubbles in this key space tree routing table, we can achieve O log n lookups, which you can probably see right behind me here. Okay, so that's distributed hash tables. But I even want to go a little bit deeper. So we want to look under the hood here. When we started the Daemon process, we began this bootstrapping phase. So in IPFS, or in this Kubo node, we have six hard-coded bootstrapping nodes. That's just the entry point to the network. You can override it with your own nodes, but usually you use these hard-coded ones, which are operated by protocol labs. And what we do when we bootstrap our node, or when we start the Daemon, we calculate the hash of our own peer ID, which just gives us here this long string of bits, and also prepare a routing table here at the bottom, which is this white box. And in this routing table, we create buckets, bucket 0 until bucket 255. And in each bucket, we group other peers that share a common prefix with our own bit string here. So what we do is we ask the bootstrap node if it knows any other node that whose peer ID start with a 1 in this particular case, because if it starts with a 1, we wouldn't have a single prefix bit, and we would put those nodes here in bucket 0. Then we ask this bootstrap node for nodes with that start with 0, 0, and we put it in bucket 1, and so on and so forth. And this process, this routing table construction and maintenance is done by all nodes in that network. And this is actually this tree-based thing that I just showed you earlier in the bottom right. So we know nodes from different areas in this key space in a very clever way. And if we now want to retrieve content, well, we run this command here at the top, IPFS get, and then the CID. And IPFS takes the CID, hashes it. We again get a long string of bits, 256 bits in this case. And then we locate the appropriate bucket. So where does this hash fall into? And we see we have 0, 1, 1 at the beginning of our hashed CID. And this will fall into our bucket 2, because we have only 2 prefixes here. And then we located the appropriate bucket, then we take the peers that we have in that bucket, and we start just bombarding, well, not bombarding, but we start parallel requests to those peers. If they know if they know anyone if they know the provider record for the CID, and if the peer knows that CID, they just return the provider record, which is the mapping from CID to peer ID. And if that peer doesn't know the CID, it just returns a list of closer peers. So I just told you that we have this XOR distance metric, and so we have, and then we can start the query again to these closer peers, and eventually end up, hopefully, finding those peers. Sorry, the provider record. Publishing content is actually pretty similar. So publishing content means we have added a file and now want to announce it to the network so that other peers can find us as a host. We again hash the CID, locate the bucket, get a list of those peers. We start parallel queries, but instead of asking for provider records, we only start asking for closer peers. So do you know closer peers? Do you know closer peers? And we end this process until the 3 peers that we currently know in this query, the 3 closest peers, have been successfully queried and haven't responded with any peers that are even closer. And this is the termination condition, and if this is satisfied, we store this provider record, again, CID to peer ID mapping, with the 20 closest peers that we know, and it's 20 because we have peer churn. So this was the technical part. And let me just summarize that again. On the left-hand side, we have the provider, and on the right-hand side, we have a requester. The provider adds a file to its own IPFS node, looks in its routing table, gets redirected to a closer node, to a closer node, to an even closer node, to that CID. Eventually ends up at a single node, well, at a couple of nodes, then stores the provider record. The CID is transmitted off-band to the requester through some other means. Something that I haven't mentioned, the IPFS daemon also maintains long-running connections to other peers and constant connections around a couple of hundreds. And the first thing that this requester does is just optimistically ask, hey, do you know it? Do you know that CID? And it's unlikely that another peer knows a random a random hash, but it could be. So let's imagine they don't know that CID, so we start the same procedure. We look in our routing table, we get redirected to an even closer peer, and eventually end up at the same peer, or well, one of those 20 closest peers to that CID, get the provider record, and actually do this lookup again to map the peer ID to the network address, and then we can transmit the data. All right. So this was the technical part of the talk. Let me just give you a brief overview of my measurement campaign, or our measurement campaign. So this is a quite involved process. So does it actually work? Is it fast? What's going on there? For our measurements, we implemented 3 complementary methodologies that cover the entire operational spectrum. But in this talk, I have only time to cover one of those. So this is the crawls. So we did these network crawls. We used the DHT to just enumerate through all the nodes in the network and just gather information about what versions they are running and so on. I will get to this in a second. Then we did probes. So we deployed IPFS nodes all around the world, requested content, provided content, and just measured the publication and retrieval times. And also logs from these gateways. So if you remember, we started the IPFS daemon, and at the end there was a gateway that was opened, and the logs of these requests to these gateways operated by protocol labs we have also analyzed. We did continuous network monitoring through crawls, as I said, and we crawl the whole network every 30 minutes. When we published this data, we had 9,500 crawls by that time, but this probably double that by now. We did a detailed analysis on this shaded area here, right behind me. And so you can see the time on the x-axis and the number of online IPFS nodes. And crawling the network is actually quite important because, and especially this tool that we have used here, this Nebula, that's what I developed, and this also monitors the uptime. And if you've been to the streamer talk yesterday, Matthew, you mentioned that peer churn is actually a quite difficult thing to cope with. So this is one of the most important metrics in a peer-to-peer network. So this tool allowed us to actually measure this peer churn. And this is a graph that shows the uptime at the x-axis and the percentage of peers on the y-axis. And the way that you read that is as follows. So we can have a look at this 4-hour mark here, and we can see that it roughly crosses this 70% line here. And this means that 70% of all nodes that join the network have left the network after 4 hours. And if you look at the left-hand side, it's roughly half of all the nodes that joined the network have already left the peer-to-peer network again after 1 hour. And these churn rates are pretty important for DHT settings like this. I said we stored the provider record with 20 peers. Since we don't know if those peers will still be around after an hour or so, this number 20 is actually quite important. So we need this replication, which can be calculated from this peer churn. So we can do some statistical analysis on that. Also, those crawls allowed us to grab all the IP addresses of those peers and map them to cloud providers. And to our surprise, a very, very small minority of nodes is hosted on centralized cloud providers. And the most important number is probably this last line here, non-cloud, is 97%. And we used a database that's called UtterDB. So this only accounts for IP addresses that we could map to cloud providers. But I think this UtterDB is quite comprehensive. And yeah, most of the nodes back then in October last year were hosted on this Contabo GmbH. And yeah, that's quite nice. So it's very decentralized and not dependent on single cloud providers, which is a good thing. And all of this data is published on in a recent publication. So if you're into academia, have a read. And in general, some call-outs. So I will close the talk with some call-outs. Get involved. There's funding, Procollapse is hiring. If you're into research and academia, if you're a student and interested in those topics, there is this radius.space website where grants are published and you can read different measurements that we propose others can do because we are just short on capacity on some of those. And I think it's a very welcoming community, so get involved. And we do all the things in public, and yeah, we are happy to hear from you. So thanks.